Welcome to our April HMEI Faculty Seminar. It is my pleasure to introduce Professor Ian Bourg. Ian is a professor in civil and environmental engineering and at the High Meadows Environmental Institute. Ian works on a number of questions related to sort of the interface of water and other chemicals, including these types of interactions on hydrology, and then, as we will hear about today, on the fate of pollutants. Ian uses a variety of methods. Sort of most visually alluring right now is sort of molecular modeling, and so each of those little balls is a molecule in the simulation, which is, for those of us that simulate processes where we parameterize things that are less than a few tens of kilometers large, this is pretty impressive. So anyway, please welcome Ian, and we'll hear about PFASs. Thanks.
Cool. Yeah, thanks, Gabe, for the invitation, and thank you all for being here. It's a little stressful to give a talk at Princeton, because I can't embarrass myself too much compared to when I'm talking at other places. I'm hopefully going to tell you some interesting stories about PFAS, other organic contaminants, how they behave in natural systems, and how they interact with various phases. This is mostly work that was done by a couple of grad students, Jenny and Xiaohan, who have now graduated, a previous postdoc, Tom, and multiple undergrads, including particularly Emily LeMay and Ethan Suntarp, who were in CE and geosciences, who are now doing PhDs at MIT and Harvard. Cool. Yeah, as Gabe mentioned, my group mostly studies anything where there's water near a surface doing something interesting in the environment, right? Historically, we started out studying how water behaves in nanopores, right? You squeeze down water to nanoscale, and it just turns into a different fluid. It adopts different properties. That I was actually doing even at the National Lab in Berkeley before coming to Princeton. And then since I've arrived here, we've kind of started new research directions. One of the major ones has been trying to upscale things. So looking at larger scales at hydrologic processes and geomechanical processes in things like soils and sediments, but still trying to be informed by fundamental information about how water behaves at the nanoscale. And then another new thing that we've been kind of developing at Princeton is just adding organics into the system, right? This kind of area is more just water and inorganic things in nanopores, but there's also a bunch of interesting stuff that happens when you add organics. I've always been afraid of looking at organics because I was traumatized by organic chemistry in college, I guess. But then, the way we look at it, it's not kind of too scary because we're mostly looking at organics interacting through kind of van der Waals and Coulomb interactions with things and not the actual organic chemistry of things turning into other things, right? Right, okay, so within this space, we do a lot of different things. I'm mostly going to be focusing on that top corner over here exclusively, but to give you an idea of the kinds of stuff that we do in these other areas, it's things like looking at how mineral surfaces might promote heterogeneous nucleation of salt crystals, for example, or using molecular simulations to determine the colloidal interactions between nanoparticles in water. With the upscaling, it might be stuff like, this movie's a little broken, but like waves interacting with coastal barriers and the coupling between the hydraulic and mechanic properties. Stuff like looking at biofilms, so microbial colonies growing in porous media, but also being deformed by the flow. And then going into what I'm talking about today, this is an example of absorption of organic contaminants on a mineral surface. And here's another example of some organic molecules at the water-air interface in a tiny little water cluster that might be representative of certain types of secondary organic aerosols, right? So I'm going to be focusing on this mostly because I talked more about this stuff when I was up for tenure at Princeton, and hopefully if I talk about the organics, most of you won't have seen a lot of this, right? I'm not the actual one who does the work. It's mostly driven by a bunch of postdocs. I've mentored 7 postdocs over the last decade at Princeton who've been focusing more on the fundamental stuff. Minte is over there. And then a bunch of PhD students who've been kind of developing more of these like new research directions. And also a lot of undergrads, mostly through HMEI, that have been mostly interested in this area here where we do the organic stuff, because if I tell undergrads that we're going to look at water in nanopores, they're like, I don't care. But if I tell them that we're going to do organic contaminants, they're like, well, I can explain that to my parents, right? So yes, cool. The types of organics that we're interested in, the easiest one to look at is emerging organic contaminants, right? Mostly because we know they're important. We know that chemical industry is really good at like designing new kinds of organic molecules with various good properties and also nasty properties. There's like a huge kind of increase in the number of different types of organic compounds that are just produced by humans, right? Over the last decade, it's estimated that there's been about 70,000 new chemicals or mixtures that have been registered globally. If I remember correctly, the EPA receives applications for about 800 new chemicals each year, right? And they have time to test like a tiny little fraction of that. So most of these get approved with no actual regulatory testing, just trusting the person who's asking for authorization to produce them, and with very little kind of like ability to predict how they're going to behave once they affect humans or nature or the environment, right? We know that they have kind of potentially large impacts on health, right? These people in the science paper are drawing like a micropollutant affecting a fish, but there's been a bunch of work on like health impacts on humans, right? In fact, this study from a Lancet kind of family journal is estimating just for the endocrine disrupting compounds, which is a pretty small subset of like all the organic contaminants we might be interested in, when they add up all of the economic damages, they come up to something like annual cost of about 2% of the GDP, which I don't know how you can get such a large number and people aren't like in the streets complaining about endocrine disrupting compounds. But I read the paper and it all sounds plausible, right? You might argue about the dollar value that they're assigning to like lost IQ points or you know, other kind of potential health impacts, but even if you shrunk all the costs by a factor of 10, this would all still be like a big deal, right? Right. And then finally, this is very complicated. It involves understanding how organic contaminants are kind of like interacting with an organism. And I like to do easy stuff and not hard stuff because, I don't know, I guess I'm kind of lazy. So we're starting by looking at much simpler things. So not how a micropollutant might partition inside a fish and might be kind of transformed by the fish, but just trying to understand how they move around in the environment and how they preferentially partition between different phases, right? So like if I release one of these micropollutants into the water, how much of it is going to go in the air? How much of it is going to stick onto some soil particles? That's going to affect eventually how they move around in the environment. It's going to affect the pathways by which I'm going to be exposed to them, or maybe the pathways by which some kind of animal is going to be exposed to them. And hopefully by learning this, I'm also going to be learning some stuff that might be useful for the biological systems. Cool. I'm going to be focusing particularly on PFAS, but also other contaminants, mostly just because these days everybody in environmental engineering is working on PFAS. So because of the peer pressure, I have to do that also. But they've been in the news like crazy, and I probably don't need to tell you. This is just one example from the New York Times from a couple of years ago, where this family bought a dairy farm about a decade ago, if I remember correctly, and they were happy raising their cows. That was in Maine, and the state of Maine came to see them, after they'd run their farm for a while, and told them that they had to stop farming and kill all their cows and stuff like that because the soil was full of PFAS, right? At the time, Maine was the only state in the country where the state was actually testing soils, right? And so like we have no idea what kind of PFAS is present on farms like in the rest of the US, right? They started suspecting that maybe the health issues that their kids were having was because of eating all the nice kind of like organically grown meat and like milk that they were actually producing, right? And it seemed like the issue was that the previous owner of the farm had been, to fertilize the fields, had been spreading sludge from a wastewater treatment plant on the fields as a kind of like green fertilizer without knowing that it had like relatively high levels of PFAS, right? These days, right, there's been a lot of work coming out about kind of like how much of it is present in our environment, and I just want to highlight this study that came out from the New Jersey Department of Environmental Protection about 6 months ago. that actually Jenny was a previous PhD student in my group, who is now working for the NJDEP. She was leading the effort to essentially develop the guidelines for how much PFAS you're allowed to release in the environment if you're in New Jersey. And as a starting point of setting the new guidelines, they needed a baseline of what's the natural amount of PFAS, well, not natural, but what's the current amount of PFAS in soils in New Jersey. So they went around and tested a whole bunch of clean soils. So these are not like Superfund sites, it's just like random farmland and stuff. And they're finding PFAS everywhere in New Jersey, right? Except maybe in some parts of the Pine Barrens, maybe. Like if you live right here, you might be okay, right? But everywhere else, the soils in New Jersey are completely contaminated, which makes it hard for the regulatory agency to tell people not to release PFAS in their environment if there's already a ton, right? But there's a weird thing going on here, which is that, typically if you saw this and you said this compound is all over the place, that would be the signature of a compound that moves very freely in the environment, doesn't really stick to soils, for example, right? If you release it, it's going to travel through the water, it's going to travel through the air, and you're going to find it very kind of homogeneously distributed, right? Whereas what these people are saying is you bought a farmland where PFAS was spread on the farm 10 years ago, and they're still finding it there, right? So clearly, we need to understand a bit of something about how the compounds are moving around and how they're, sticking to the soil minerals, floating around in the water, evaporating into the air, in order to basically understand how the things move around, what's our most likely exposure pathway, and what might be the most kind of appropriate remediation technologies. And that's the kind of stuff that we're actually just kind of starting to find out now. So as a proxy for soils are super complicated. And we're just using one type of clay mineral that's present in soils. This is smectite clay as kind of a generic soil mineral, right? And we're going to try to see if we can predict how PFAS and other contaminants might stick to these minerals, right? So in case you don't know, this is basically one type of clay mineral. It's the main clay mineral in soils of the western half of the US, particularly in semi-arid and semi-arid regions. On the eastern side of the US, there's more illite clay, but that has a very similar structure, right? It consists of natural nanoparticles that are about 1 nanometer thick, a couple hundred nanometers in diameter. Because they're so tiny, they have a really high specific surface area, right? And also, they have a high cation exchange capacity. There's a lot of negative structural charge inside this mineral, right? And that's coming from the structure here. This is one of these layers. You have to imagine it's much wider in the horizontal direction, but it's just 1 nanometer thick. It's mostly silicon, oxygen, and aluminum, like the 3 most abundant elements in the Earth's crust, right? And those 3 elements, they can form this really nice and stable motif. So you end up with half of the minerals near the surface of the Earth being based on kind of this layered silicate structure, right? They're exposing this huge surface area that's mostly these planes of oxygen atoms over here. And they have a high amount of negative structural charge that's coming from these isomorphic substitutions, where in this case, an aluminum's been randomly replaced by a magnesium. So you go from +3 to +2. It gives you a -1 charge, kind of randomly distributed in the mineral. But because the overall structure is so stable, it doesn't blow up the mineral, right? And then this negative charge of the mineral is charge balanced by some adsorbed cations, like these blue spheres here, mostly sodium and calcium in most kind of soils and sediments, that just kind of have to hang out near the mineral surface to charge balance it, right? Because of their high aspect ratio, they tend to form stacks of parallel particles, but because they have these cations near the surface with a relatively high hydration energy, you tend to get propped open interlayer space here with water inside, right? Water and ions. And in the case of certain kinds of clay minerals like these smectites, the amount of water in this interlayer space is going to be highly variable depending on how much water is in your environment, right? So depending on your relative humidity, you're going to get expansion and shrinking of this interlayer space and some kind of interesting mechanics, right? This is just an illustration of what that looks like in a cryo-TEM, where the horizontal scale of the image is about 200 nanometers, and each of these is one of these 1 nanometer thick particles, right? So again, in soils, at least in temperate regions, this is the main kind of mineral, right? This structural motif here, either in smectite or illite, is typically about half of the mineral mass in your soils. And because they're typically more fine-grained than most of the other minerals, they're contributing 98 or 99% of the surface area, right? So most of the fluid in your soils is going to be in contact. If it's in contact with the surface, it's going to be touching this plane of oxygen atoms. And most of the solutes, like organic molecules, if they're near a surface, they're probably going to be near this surface, right? If you have high abundance of smectite, you get this kind of like iconic desiccation cracking from like swelling and shrinking every time it rains. Right? Same thing if you're standing on top of a sedimentary basin, roughly half of the rock mass under your feet is this type of mineral, right? And so most of the fluids that are in your sedimentary basins, if they're interacting with the mineral surface, it's going to be that kind of stuff. Cool. And then the tool that we're going to use is molecular dynamic simulations, as Gabe already alluded to. So we're basically just solving Newton's equations of motions for assemblages of spheres that are interacting through semi-empirical interatomic potentials, right? We could use quantum mechanics to predict the interactions between atoms, but that would be crazy computationally expensive, and we'd be limited to simulating maybe like a few hundreds of atoms. Instead, we'd like to simulate millions of atoms, and so we use just kind of semi-empirical models that just say if an atom of type A is at a certain distance from an atom of type B, they attract each other or push each other away with like a certain force, right? Of course, that means that the predictions that we get are going to be sensitive to kind of like how much do we trust these semi-empirical models, right? But at least for these kinds of minerals and water and organics, there's quite a bit of accumulating evidence that we can get decent predictions in a lot of cases. The main other limitation is because we're trying to solve for like the dynamics of each atom individually, even with kind of simplistic models of the interatomic interactions, we're still limited in kind of time scale and length scale, right? So we're going to see things on length scales of nanometers and time scales of nanoseconds, and then we're going to hope that the information that we can get here maybe translates to larger scales, right? That's a pretty big leap of faith, right? But it's also a good reason for us to just kind of start by looking at maybe like equilibrium constants, right? Because some kind of like the Henry's law constant that determines partitioning between water and air of some kind of organic molecule, presumably it's like a thermodynamic constant that should be the same at the nanoscale and at the scale of a global simulation, right? Cool. Yeah, so this is the kind of stuff that we can do, right? Jenny was a PhD student in the group who is now at the NJDEP, as I mentioned. She decided on some day to study how phthalate esters would interact with soil clay minerals, right? And at the time I was like, what's a phthalate ester, right? But these are some of these endocrine disrupting compounds that are apparently like causing a huge amount of damages to the health of the US, right? And in this case, she's modeling a system with just two little mini clay particles, right? The real ones would be still 1 nanometer thick, but a few hundreds of nanometers horizontally. There's water everywhere. There's maybe like a region over here with a bit more water. It's a periodically replicated system, so if something goes out one side, it comes back in the other side. The clay is negatively charged, so the blue spheres are these counter ions that have to charge balance the clay. And then she puts in 3 of these little phthalate ester molecules. And if you run a normal MD simulation, once the organic molecule finds the surface, it just spends the entire simulation there, right? It just kind of moves back and forth on the surface, which is, it tells us that the compound likes to be adsorbed. It just doesn't tell us how strongly, because in order to quantify the strength of the adsorption, we'd need to see it attaching and detaching multiple times, right? So what Jenny's doing here instead is using a method known as metadynamics, where instead of solving Newton's equations of motion, it's solving a kind of biased version of them that pushes the organic molecules around, forces them to explore the entire space, and then this is just a few tens of picoseconds of simulation, but this is showing over 200 nanoseconds how the system is kind of progressively discovering the free energy landscape, right? So it's progressively discovering these dark blue regions that are the regions where the organic molecule really likes to be, right? And then eventually, if we compare the color, say, like far from the surface and the color near the surface, we can see both where on the mineral surface the compound likes to adsorb and also exactly how strongly, right? In the case of this molecule, we find the color difference gives us a free energy of adsorption of about 1 eV, which is about 100 kilojoules per mole. So the compound really likes to stick to the mineral, right? If we released it into soil in the environment, it would spend very little, only a tiny little fraction of its time in the water, right? Cool. Yeah. There's 6 phthalate esters on the EPA's priority pollutant list out of like 130 compounds, if I remember correctly, right? And so Jenny's just here looking at this free energy landscape for all 6 of those on the same kind of stack of 2 little mini smectite clay particles. And the main thing that you can see here is going from the smaller one to like larger and larger ones. The lengths of these alkyl chains is increasing, right? And then these dark blue regions are becoming darker and darker. So as the molecule is getting bigger and bigger, And especially as we're growing, it's kind of like hydrophobic alkyl chains. It's telling us that it would like to stick more and more strongly to the mineral surface, right? In fact, we can take this information and turn it into a KD coefficient, so like an absorption coefficient for partitioning between the compound in water and the compound on the surface on a log scale here. And we're plotting it here for the 6 phthalate esters, for 3 polycyclic aromatic hydrocarbons, and for 1 PFAS over here. And you can see, for example, molecular weight seems to be a thing that's playing an important role in determining the tendency of the organic molecule to stick to the surface. In fact, right, this is a log scale, so it's like a huge range in like affinity for the surface, right? A log KD of 0 would mean if I have a kilogram of my clay and a liter of water, and I add my organic contaminant, it's spending about half of its time in the water and half of its time on the mineral, right? Whereas a value of 9 over here would mean what, like, it's spending 1,000 million times more of its time on the mineral than in the water. So like, this compound is never, practically like never in the water, right? Molecular weight seems to play an important role, and basically a compound that's lighter than about 100 daltons, we would expect that it would be mostly dissolved. And a compound that's heavier than maybe like 200 or 300 daltons is going to be mostly like on mineral surfaces in the environment, right? That's actually just a small number of contaminants, but it matches what's been observed experimentally for like nitrotoluenes, PCBs, pharmaceuticals, right? This is why like in the Hudson River, you still can't eat the fish that you catch there because the sediments are still contaminated by PCBs that General Electric released like 70 years ago, right? And they're sticking so strongly to like the soil minerals inside the sediment that they never go away, right? Cool. One thing that this suggests is that the compounds, this is what you would expect if the affinity of the compound for the surface was actually driven by hydrophobicity, right? Like not the compound being attracted to the surface, but water wanting to spit out the compound, right? Because a bigger and bigger compound is kind of disrupting the hydrogen bond structure of water more and more. And so a bigger and bigger organic molecule should be less and less soluble in water. And so like you would expect this kind of trend if the compound even like had no preference for being like near the solid, because its preference for being in the water would decrease quite rapidly as it's getting bigger, right? It's kind of weird because when people talk about organic molecules sticking to things, usually they assume that there's like a functional group on the surface of the organic molecule that likes something on the surface, and that if you design that stuff, you can get a better adsorbent, right? But this seems to, it's also consistent with what you would get if it was a fully kind of like non-specific thing that has to do with the fact that water doesn't like to hold things that aren't polar, right? Yeah, we can zoom in a bit more and actually get a vision of that from the simulation, right? Because when a compound is near the surface, I can calculate its potential energy, right? I can calculate, say, like, what's its potential energy of interaction with all the other atoms in the system. I get that for free from the simulation because the code is calculating that to solve the equations of motion, right? I can do the same thing for the compound far from the surface, and then I can get a difference in potential energy. That's basically going to be a kind of like heat of adsorption of the compound on the surface, and it's going to tell me how much of that free energy of adsorption is driven by the compound itself wanting to be near the mineral, right? And then by subtraction, I should be able to say, like, what's the rest of the free energy of adsorption, the part that's not being driven by the molecule itself, right? If I do that for these 6 phthalates, I see, okay, that kind of change in potential energy as the compound goes from water to the surface is negative, so it's favorable, right? It prefers to be on the surface, but if I calculate the rest of the contribution to adsorption based on my knowledge of the free energy, that contribution is tiny compared to the rest, right? And again, that doesn't match what people kind of like hypothesize when they look at organic molecules and wonder whether they're gonna stick to minerals, right? Just an example, this is a classic cartoon of how natural organic matter might interact with different minerals in soils like smectite, iron oxides, kaolinite, and stuff like that. And the authors are hypothesizing that certain functional groups in the organic molecule are attracted to specific minerals because they like to interact with certain parts of them, right? Which completely does not match with what we're seeing here, right? Cool. For PFAS, I probably should not spend too much time on this because we see the same thing. This is, PFAS are a bit different because they're anionic molecules, so we would expect them to be repulsed by this negatively charged mineral. If we use this metadynamics again to map the free energy distribution of the PFAS on the surface, again, we see a more negative free energy near the mineral surface. That's telling us that the compound likes to be near the surface. Jenny did a little bit of something extra here, which is that in addition to these metadynamic simulations where we push the compound around and ask it to report the free energy, she ran some classical MD simulations where she just places a PFAS molecule on this surface over here where we know that there's a really high affinity, right? And she just lets it do whatever it wants, right? So it's gonna move back and forth on the surface. There's a really deep free energy minimum here, so it's not gonna detach from the surface, but it's gonna explore the entire space. And then over here, she's mapping out the density distribution of the PFAS in this region over here on the surface, right? And so you can see that the lighter color is where the PFAS is spending more time. And it's not uniformly exploring the surface, it's preferentially spending all of its time in a few little pockets on the surface, right? Actually, this pocket overlaps with that one because the system's periodically replicated. What you need to know here is these little white diamonds, they're the location of the negative charge sites from these defects in the nearby mineral, right? So the PFAS is basically gliding around on the surface, but only in the pockets on the surface where there's no structural charge, right? Which makes sense because that's the more hydrophobic part of the mineral surface, right? Where there's charge, there's going to be more polarity on the surface. There's going to be a counterion that's going to be hanging out there with its hydration waters. But yeah, it looks like the compound is basically finding little hydrophobic pockets on the mineral surface, and that's driving a very large affinity for the surface, right? Weirdly large. And it's also weird because in general, people think of these clay minerals as being hydrophilic, right? You expose them to water and they swell. Clearly they're like sucking up water. They must be like a hydrophilic material. And yet somehow at the molecular level, there's these tiny little hydrophobic pockets that are kind of completely dominating the absorption of these organic molecules, right? Dominating the absorption of organic contaminants and probably dominating the way that like natural organic matter would interact with these minerals in soils. Which brings me to soil carbon, right? Like if we can get some insight into how organic contaminants interact with these minerals, and this is like, 98 or 99% of the mineral surface area in most soils, then we should be able to say something about how like natural organic matter is going to interact with soil minerals, right? It turns out, okay, there's a ton of organic matter in soils, right? There's about as much as the atmosphere, the biosphere, and the surface ocean combined, right? This soil is going to be, well, I don't know about this soil specifically, but a typical soil in the US is going to be about like 50% clay minerals, but there's going to be probably like several percent organic matter. If that organic matter is interacting with these minerals, something interesting should happen from that interaction, right? We know that this is a huge reservoir of natural organic matter with huge impacts for like the carbon cycle, for soil fertility, for soil resilience to erosion and drought. And we also know that the fluxes of carbon going into soils and coming out of soils each year are like ginormous, right? This is about what, like 6 times larger than the anthropogenic emissions, right? Because it's gigatons of carbon, right? So plants are constantly pumping in a huge flux of carbon into soils, mostly as things like sugars and waxes that they're pumping out through their roots to manipulate the chemistry of the soil around them. But then microbes are constantly respiring that carbon and turning it back into CO2 with fluxes in both directions that are like, what, 5 or 6 times larger than our anthropogenic emissions. It would be nice if we understood a little bit better kind of like what controls these fluxes, right? Like what controls the amount of time that these organic molecules spend in soils before they get turned back into CO2 by microbes, right? I guess in the last kind of roughly decade, it's been kind of emerging that a lot of this soil organic matter, probably at least half of it, consists of relatively small organic molecules that, like, if you study them in the lab, microbes respire them within like days, right? Compounds with molecular weights on the order of like 200 or 300 daltons, right? But if you put them in a soil and you do the carbon dating, it looks like they have lifetimes of decades or hundreds of years, right? We have no idea what is causing this, but there's been a few meta-analyses that came out in the last decade of like trying to look at all the information they could find on all the soils worldwide and looking for correlations. And at least in temperate soils, the strongest correlation that they find is that the abundance of these smectite and illite clay minerals seems to be the main thing that where you can identify a correlation with these fluxes of organic carbon, right? It's not all the correlation. It explains, if I remember correctly, about like 30% of the signal. But it's a clue that the minerals are doing something with the organic matter and affecting kind of like the rates of microbial respiration, right? Maybe the same thing that they're doing with the organic contaminants, like we have no idea, right? Cool. We've been trying to work on this. It's just tricky because there's no well-known structure of soil organic matter, right? An organic contaminant, we can look it up and be like, this is the structure, and then we can construct it and put it in a simulation. As a molecular modeler, if you want to study soil organic matter, you need a plausible structure, and then everybody's going to criticize you for like, picking this structure instead of that one, right? We're working with one that was developed by some people at the Oak Ridge National Lab a few years ago. It's a mixture of about 20-ish different organic compounds that when you mix them together, it looks like various well-characterized kind of like experimental proxies. What they did mostly with it is take this mixture, stick it in water, and they see that it clumps together and forms micelles with the organic moieties towards the inside and the hydrophilic, with the hydrophobic moieties towards the inside and the hydrophilic ones towards the outside, right? What we've been doing is doing the same thing but near mineral surfaces, right? So this is a mineral surface. We've done this with goethite and smectite, right? Over here, there's water that we're not showing, and these are organic compounds, and over here, there's air. And what we consistently see in these systems, you have to kind of like equilibrate them carefully, because once the organics clump together, you don't want them to be kind of like frozen in an unphysical way. But what we consistently see is like some organic molecules that are just floating around in the water, some organic molecules up here that are sticking to the water-air interface that you can't see because it's so faint, and then a bunch of organic molecules that are forming a kind of hydrophobic clump that's trying to coat the surface, but is coating it in a very uneven and kind of like blobby way, right? And there's some dynamics of organic molecules attaching and detaching from the water-air interface and the surface coating, but obviously once you have this, there's all sorts of stuff that you can analyze. Kind of like the top line result is, this is these 20 different organic compounds plotted as a function of their molecular weight here. And what we're showing here is the percentage of time that they're spending in the organic coating on the surface versus in solution, right? And so you can see again, the molecular weight seems to be the main thing that's kind of like controlling whether or not the compound is in the coating on the surface or floating around in water, right? There's like some slight details in where like neutral molecules maybe stick more to the surface than like anionic molecules, right? These things have a bunch of carboxylic groups. But mostly a compound that's less than about 100 daltons is going to be more dissolved most of the time. And a compound that's heavier than about 150 daltons is just going to be coating some kind of mineral, right, again. And again, it looks like the hydrophobicity is driving this, or it's consistent with hydrophobicity. This time for like clustering of DOM molecules and coating of surfaces. But kind of like the same thing that we saw for organic contaminants just interacting with the mineral, right? And it kind of mostly matches like current theories of dissolved organic matter, except in one sense, which is, this is kind of like the main one right now, where the hypothesis is that if you start with large organic molecules and they're progressively broken down in soil into like larger biopolymers and then smaller ones and then smaller ones and then eventually into CO2, the current kind of like hypothesis is that as the compounds are getting smaller and smaller, their interactions with mineral surfaces or their tendency to kind of clump with other organic molecules is getting more and more important. And what we're seeing is it looks like that might be true down to a certain cutoff, but definitely once you get lighter than about 150 daltons, then you're not going to want to interact with the mineral surfaces anymore. You're mostly going to be floating around in water and maybe much more bioavailable to microbes, right? So somehow, if they can break down things down to like a certain size cutoff, then they should be able to accelerate the cycling of organic matter, right? I'm going to quick wrap up with like switching gears, right? The absorption on soil minerals is kind of like fun, but it's also a little bit complicated because the minerals are kind of like exposing different facets, and you've seen for these stacks of clay particles, there's like external surfaces and internal ones and stuff like that. It's also quite kind of computationally expensive and tedious to try to map out how the organic molecules are interacting with different parts of the surface, right? So during COVID, I recruited I think like 8 or 10 undergrads to join the group through the HMEI summer internship program, because all of them were having like their internships being canceled, and they were like, what can we do? Do you have any ideas of internships? And I was like, well, through Zoom, I can teach you how to do molecular modeling, right? So there were all these undergrads in the group that were basically constructing input files for organic contaminants. I was like, well, we're going to make all these input files for like 100 different organic contaminants. We're going to post them on GitHub, and then other scientists can do cool stuff with it. But then Amelie and Ethan were like super motivated to continue doing research, and so we figured, well, instead of just posting this information for other people to use, let's write a paper where we're doing something with all these organic contaminants. And the idea that we came up with was to like study how they behave in the simplest kind of system that we could think of, the simplest multi-phase system that we could think of, which would be a system where there's there's a water here. This is just a slab of water, right? It's kind of connecting to itself through the periodic boundaries, right? And then here there's a slab of void space, which is quite a good proxy for air, right? So this is an extremely simple interface, right? It's just a water-air interface. We should be able to just throw in one organic contaminant in the system and see, like, does it prefer to be in air? Does it prefer to be in water? Does it prefer to be, like, interacting with the surface, right? There should also be quite a bit of data on the Henry's law coefficients that we can use to validate this. And we know that there's very few data on adsorption at the water-air interface, so we can maybe generate new information about some property that people don't know much about. When we started doing this, we bumped into the same issue that we had with the clay, which is that once you add the organic molecule into the system, for most of the compounds that we were looking at, once it finds the interface, it just spends the entire simulation there. And we're like, oh great, it likes to be at the interface, but I can't quantify like how much, right? It's just like a lot. And so what we're doing here, at least it's instead of being a two-dimensional free energy landscape, it's just in 1D, right? So all we need to know is like how free energy changes as you go from here to here to here, right? And then once we have that, we're gonna know the preference for, right? And so there's a simple tool that you can use to determine that, which is that you tether the compound at a whole bunch of different locations along that one coordinate, right? So instead of letting the compound be at the most favorable position, you force it to be at a slightly unfavorable position, and then you let it kind of report to you what it's feeling, right? So for example, here, this is an organic contaminant tethered like right above the surface. It would like to go right? And it should be able to report that to us. And here's one that's tethered right underneath the surface, and it probably wants to go left, and it should be able to report that to us. But that allows us to sample essentially kind of like configurations that are unfavorable that the normal simulation wouldn't sample, right? Because of the very short time scale of these simulations, right? So this is, again, an illustration of this. If I take a simulation like this, and I put a compound here, and I just run a normal MD simulation, I can calculate how much time the compound spends at any location, and I'm gonna find that it spends all of its time right at the surface, right? That tells me like there's a free energy minimum somewhere over here. In fact, I can characterize the shape of that free energy minimum by just using this relationship that just relates the free energy of the system in some state with the likelihood of observing the system in that state, right? So the natural log of this probability distribution, I just take minus RT, and it turns into this free energy minimum here in black, right? It's nice, it tells me the shape of the free energy minimum at the interface, but it's super noisy around the edges because I'm not sampling here or there, right? I'm not sampling the unfavorable coordinations. The gray line here is what I get if I tether the compound at a whole bunch of different locations. Each time it's giving me like a little piece of the free energy landscape, and then I can stitch them back together. So I can see free energy going from a stable free energy in air to the minimum at the interface, and then a stable free energy in water, right? Now I can calculate the affinity for the interface and also the relative affinity for the two fluids, right? Cool. Okay, what we see is like there's always a minimum at the interface, right? Like all these compounds here, they all, they don't like to be in air that much. They like to be in water more, but they like most of all to be like right at the interface, right? These charged compounds over here, same thing, except they really don't like to be in air because they like the high dielectric kind of like constant of water, right? But they still like most to be at the interface, right? All of these compounds here, most of them have a free energy minimum at the interface, right? These undergrads are awesome. Like, I would not have done all this by myself, and all these compounds also over here, right? Like glyphosate, this is like Roundup herbicide. There's like billions of dollars of like lawsuits. Permethrin for like killing ticks, and some kind of PFAS and PAHs, aspirin, PCBs, what is this? This is like a lily of the valley scent, right? If you're using some cosmetics, except it's banned in certain countries because it's bad for you, right? I think in the US it's like legal, but cool, okay. They all like to be at the interface. What that's telling me probably is like any water anywhere in the environment is gonna have a coating of organic matter on it, right? The surface of Lake Carnegie, there's probably like a layer of organic molecules on the surface. If I pour myself a glass of water and I put it on a table for about 10 minutes and then I drink it, there's probably like a whole coating of like whatever was in the air is like accumulated there, right? Maybe I'm getting exposed to organic molecules through that even though I filter all my water, right? Okay, the codes seem to work. This is our MD predictions of the adsorption constant for attaching to the surface, going from water to the interface. these are the few compounds for which there's actually experimental measurements, and it's falling nicely on a 1-1 line. There's experimental data for some of the PFAS, and we're matching nicely, right? That also matches kind of recent observations that, like in coastal regions, one of the major sources of PFAS is from sea spray, right? Like there's PFAS in the ocean, and then there's bubbles of air that get trapped underneath the ocean because of the wave action, and then those bubbles come back up to the surface and burst, and they're ejecting aerosols that are all coated with PFAS. And then the people in these coastal regions here in Norway, most of their exposure to PFAS is coming from like the sea spray, right? But then like some of these other organic contaminants have affinity for the interface that's just as high as some of these PFAS, right? I think this is like a chlorinated organic molecule. And so for PFAS, it makes sense because we think of them as being surfactants and liking the water-air interface. But there's probably like other organic contaminants for which this is also like a significant source of like human exposure, right? Or moving around contaminants in the environment. Should I even talk about this? Okay, one potential interesting kind of like side implication is like the affinity of organic compounds for the water-air interface like also has implications for, say, like understanding secondary organic aerosols, right? Like this is a major source of uncertainty in estimates of the effective radiative forcing over here, right? Most of the error bars of like the total estimate is coming from like uncertainty about aerosols, right? And a large part of this uncertainty is coming from the fact that we have a hard time kind of predicting the nucleation of secondary organic aerosols, right? So this is like, you know, the atmosphere being full of molecules that maybe could condense, like water vapor and volatile organics and maybe some ions. Mostly when they collide together, they form unstable clusters because there's like too much surface tension for the cluster to be stable. But if they can reach a certain size, they can get over that like activation hump and form a stable cluster that then is going to kind of persist in the atmosphere, maybe like later turn into like a cloud condensation nucleus or something like that, right? But there's like a huge amount of difficulty in kind of predicting the nucleation rate of these critical clusters because there's a lot that we don't know about what's going on at the molecular level here while these unstable clusters are trying to turn into stable ones, right? We've done a little bit of looking at this because this is a length scale that we can kind of like easily study with our kinds of tools. And what we're seeing here, this is Xiaohan, who then continued with a postdoc at GFDL, was looking at clusters formed of water and a dicarboxylic acid that might be representative of some semi-volatile organics in the atmosphere, right? Again, the surface tension of the cluster is the main thing that's making it hard for the cluster to like form a stable, reach the stable size, right? And what we're finding is the surface tension over here is highly dependent on, let's see, the dark blue circles are surface tension of the cluster as a function of the number of water molecules in the cluster for a pure water cluster. And so you can see that as the cluster gets smaller, the surface tension drops. And then the colored symbols over here are adding organic molecules in the cluster is also lowering the surface tension, right? Okay, so that makes sense. The size dependence, I don't know, but the addition of organic compounds to the cluster is lowering the surface tension. Maybe that makes sense, right? If we take this and plot it as a function of the ratio of mass of organics to mass of water, there's this weird kind of like transition point over here where you're right at a mass ratio of about 4.5, right? Where one of these little clusters here that's mostly water has a high surface tension of water. A cluster that's mostly organics is approaching the high surface tension of the organic phase. But a cluster that's just at a certain ratio of water to organics has a much lower surface tension that might help like these secondary organic aerosols to like nucleate and reach that stable point, right? And what seems to be going on here, if we take a whole bunch of these different clusters with this 3 nanometer diameter with different ratios of organic to water, is that there's a weird morphological transition right around that point where on the one side you have a nice well-mixed mixture of organics and water, and on the other side you have the water is all clumping together in the core of the cluster and being coated with the organic molecule, right? So again, I don't know how that, you know, somehow this transition to the organic being absorbed on the surface of waters may or may not be playing a role in kind of like dictating the ability to nucleate new secondary organic aerosols like in the atmosphere, right? We need to work on this more, except unfortunately Xiaohan decided to leave the group and work on kind of like modeling aerosols at much larger scales. So yes. Cool, these people do all the work. I just get to have fun chats with them. And these people have supported all this for way too long, I think. But yes, thank you for your attention.
All right, folks, so we're getting to the Q&A stage. So Hina's going to join me over here. For those of you online, I will receive messages on this computer here. And Ian just talked for a bit, so he needs some break. But the first question from the audience or online, do we have a student or early career scholar with a question?
Ian, thank you for that talk. You talked about equilibrium partitioning coefficients. I was wondering, is there ever a case where non-equilibrium or transient effects are of interest for these systems?
Yes. I mean, especially the stuff that I was mentioning at the end, for example, if you look at the, like for the distribution of organic molecules in soils, probably things change slowly enough that you can probably assume that you're always kind of like, that you only care about being near equilibrium, right? But if you look at some of the models that people are developing to try to understand the ability of tiny little clusters of water vapor and organics in the atmosphere and ions to grow enough to form stable particles, definitely a lot of the models that people are building right now, the kinetics seem to be important, right? Like you have a cluster that's trying to be stable, and then some organic molecule lands on the surface of it. And it's kind of like, well, is the time scale of that molecule redetaching from the surface and flying off into the air? How does that compare to the time scale of it kind of diffusing deeper inside the cluster, that kind of stuff, right? We have a challenge with the simulations, which is that, as I mentioned, like often when we're modeling systems where the free energy landscape is not too hilly, where there's not like a big barrier between two different favorable states, for example, right? I can run a normal simulation where I'm just solving the equations of motion, and it correctly kind of like samples the relative likelihood of finding the system in certain states, right? But then for some of these other systems, in which case I get both the thermodynamics, I guess, and I get the relative stability of different states, and I get the kinetics for free because I'm solving Newton's equations of motion, right? Unfortunately, there's like these other systems where there's free energy barriers that are too high. There's like stuff that I would never see happening unless I kind of use these tricks to force the system to, like this metadynamics tool where I'm forcing the organic to tell me where it would like to absorb, right? And at that point, I get the free energy, but I'm biasing the dynamics, which means I'm not getting the real kinetics of the system anymore, right? You can try to like infer them, but like it starts getting a little tricky. Yeah.
So I think I saw a hand here, and then there, and then there.
Ian, great talk. I was wondering about the scale-up process. So since you're simulating in angstroms, and if you scale it up, say, to a meter scale soil, I wonder, adsorption comes as a source term or a sink term for solute transport or reactive transport. I wonder how much water versus air is present in the vicinity of your molecule. How does that affect the adsorption? And can that change the effective solid or the porosity of that medium?
Yeah, I mean, that's a good question. Like it's, I guess my philosophy would be that if I'm determining some thermodynamic kind of equilibrium constant, then that should still be valid like at all scales, right? On the other hand, like you're saying, there could be other stuff that happens at scales that I can't capture that mean that thermodynamic constant doesn't actually get expressed, yeah, at a scale larger than if I'm simulating a soil, at least using these tools, it's like a 20 nanometer chunk of soil, right? And so I'm not capturing the heterogeneity of my soil at larger scales, the distribution of, if parts of my soil are dry and parts of it are wet and parts of it have roots in it and parts of it have like, microorganisms, that heterogeneous distribution is presumably going to affect stuff and mask the effect of my nice equilibrium constants, right? But yeah, yeah.
Interesting. Thank you.
So we have a question there, and then there's a question back there, man.
Hey, Ian, great talk. Over here. Sorry. I have a question about force field parameterization for you.
Yeah.
So did you kind of re-optimize transferable force fields here, or use like MLIPs? I guess I'm wondering, where did you get your parameters from? How did you choose them, especially when you were like scanning like a pretty wide chemical space in like the latter half of your talk?
Yeah, this would not be a good MD talk if there wasn't a question about force fields. But yeah, we're in this case, like, I don't like designing force fields, because if I'm designing a force field or kind of like parameterizing it for a system that I'm interested in, I'm always then I don't know, like, if I get a good match with some kind of experimental observation, is it because I'm correctly predicting something, or is it just because I parameterize my force field to match the experiment, right? So like, as much as possible, we tend to try to use kind of general purpose force field. Like in this case, for the organics, we're using OPLS, right? And so like, it wasn't designed specifically to model organic contaminants, right? It was mostly designed to study hydrocarbons, I guess, originally in condensed phases, right? But it's pretty widely used to model even like biological molecules, and and if it does a good job for the organics, for the organic contaminants, then it allows us to have more confidence in the quality of our predictions, because we know we didn't tweak anything, right? It doesn't always do a good job. Like, I didn't show you, but for example, like for the brominated organics, the OPLS parameters do a really bad job of predicting the Henry's law constant, right? And I guess that's a good thing to know, right? They included parameters in their force field for bromine on an organic molecule, and we can see like it doesn't work when we compare it with, which is important if you're interested in like brominated flame retardants that they put like in all our beds to avoid us like dying in our sleep, right? But that are kind of like causing all sorts of, yeah. So I guess that would be my philosophy of like, using a general force field as much as possible, knowing that it's not going to be optimized for any one given system, but at least it should reasonably allow me to kind of make generalizable kind of like inferences from my results, right?
Okay, so we have a question there, and then Lars has a question, and then
Thank you so much for the talk. That was really great. My question is basically, so we know microbial biofilms are usually forming at the air-water interface. So is there a way like to tune environmental parameters so that these biofilms have more access to organic contaminants and they tend to accumulate more in the air-water interface?
Yeah, I mean, that is a very good question. Yeah, like I think the sea surface microlayer, or I guess the surface microlayer of any water body is like super interesting. And I would love to study that in the future, right? But like most of the characterizations of it that I've seen are at scales much larger than what I'm looking at, right? So like people know, like if you go and sample microorganisms or organic molecules in the ocean, you find a different mixture of organics if you sample near the surface of the ocean, right? And so there's clearly some kind of concentration gradient as you go from the surface of water into the depth, right? But what I can see is like the molecules that really have an affinity for being like right at the interface at the molecular level, right? Whereas most of the sampling campaigns, or presumably also like if you're doing a field experiment, you would be saying like there's an enrichment near the surface, but it could be, is it on a length scale of like micrometers, or like, when people describe the biological component of this enrichment, to me it sounds like they're talking about an enrichment over length scales that are much larger than what I'm seeing here, right? Yeah, I don't know. Like, I think there'd be like lots of interesting research to do about that, right? Also, kind of like what parts of the enrichment of the interface of the surface of the ocean, for example, in certain molecules. What part of it is coming from certain organic molecules really liking to be attached at the water-air interface? What part of it is coming from certain organic molecules as they try to like get mixed deeper into the ocean, they get kind of captured by air bubbles that end up underneath the water, and then they accumulate at the interface and it keeps pulling them back to the surface? What part of it is just a biological effect where certain organisms like algae that are living near the surface are producing more certain compounds? Presumably all these things are like coupled together, right? But I haven't really seen anybody who's, there seems to be a lot of people kind of like working on different pieces of it, but I haven't seen anybody who's kind of like trying to combine all the, I don't know if that answers your question at all, but like I think it's a super interesting topic.
So we have Lars has a question, and then there's a question back there that I didn't see.
Thank you, Ian. A very interesting talk. I have a question, maybe philosophical question about the scaling up part of what you're trying to do. I'm thinking if you go to what Schrödinger and company did in the 1950s or so, it took all these millions of molecules and they derived statistical mechanics or statistical thermodynamics, so simple rules that allowed you to predict what all these molecules do at the next level up. You're kind of doing the opposite. You're now saying I don't know if it's anti-Schrödinger, but you're saying, I want to account for all the molecules, right, and how they interact. And I'm wondering, when it comes to this scaling to environmental questions and so on, what do you see as the benefit of your approach relative to the standard statistical mechanics approach?
Yeah. I mean, I don't know. Like, I think, like, if you really want to be mechanistic for some of these systems, you need a multi-scale view, right? I don't think you can, especially for systems like a soil where there's biology and hydrology and chemistry and stuff like that, right? Because like you know, here we're focusing on the chemical aspects, and I feel like those are mostly happening at the molecular level, right? But then if I was just focusing on the biological aspects of what are the microbes doing that are respiring the soil organic carbon, I would need to focus more on the scale of, I don't know, like a soil microaggregate that would have a dimension of like 100 micrometers, right? And if I wanted to understand the scale, like what goes on in terms of multi-phase flow and mechanics in the soil, maybe I'd have to like be getting information from an intermediate scale, right? But then all those different physics are influencing each other, so yeah, like, but also like I think personally, the way that it took me a while to realize it, but like at some point after being at Princeton for a while, I realized like a lot of the projects that I was developing ended up having a similar kind of philosophy of starting with a kind of constitutive relation that people are using to represent the world at our scale. Like I'm using Kozeny-Kármán to represent flow in a porous medium, right? And then trying to see, well, if I got, what information would I need to get from smaller scales to improve that constitutive relation, right? And I feel like, I don't know, that's the kind of questions that attract me. I just never realized it until, you know, doing research for like 15 years and being like, I'm always asking the same kind of thing, right? Yeah, you know, like if you're plotting in some kind of equation in a global climate model because you want to understand kind of like the rate of carbon respiration at the field scale, right? You're going to say my rate of carbon respiration is going to be a function of the average soil saturation and maybe the clay content and temperature and stuff like that, right? But presumably you can kind of come up with like a constitutive model that does a pretty decent job of matching some stuff, but there's always going to be some extra information that you could get from some smaller scale that would allow you to even like slightly improve that equation, right? It's just kind of like, what do you have to go get from the smaller scale? And also then, how do you transfer that back to the scale that you're interested in, right?
So there's a question there, but first I'd like to go to the Zoom because they've been, so just here's the question is, if PFASs were not present in the soil, would another molecule be adhered to the surface? That is, are PFASs taking the place of other molecules in the soil?
Yeah.
Or
I mean, so there seems to be regions on the surfaces of soil minerals that have affinity for organic contaminants, right? And they also seem to have affinity for at least certain fractions of the soil organic matter, right? Jenny, during her PhD, her last chapter was not just looking at the absorption of organic contaminants on pristine soil minerals. It was like loading up soil minerals with mixtures of amino acids and then looking at the absorption of organic contaminants. And then, yeah, we could see that some of the amino acids were kind of competing with the organic contaminants for those preferential sites. And in fact, it seemed to kind of like even out the affinity of the organic contaminants for the surface, where instead of being dominated by the affinity for just one region or something like that, the presence of natural organic matter that was just kind of like competing meant like the most favorable sites might be blocked by a natural organic molecule, right? But then the presence of organic coatings was also increasing affinity for, and so like the affinity of the PFAS that we were seeing and the other organic contaminants for like organic coated minerals, like what you might expect more in a soil, was much more kind of like, seemed much more kind of uniform and even and easier to kind of like handle, I guess, than what we were seeing for the pure mineral, right? But the idea for the pure mineral and the fact that some patches on the surface seem to have a particularly high affinity maybe would be more relevant to somebody who wants to design an adsorbent. You know, like the patches on these clay surfaces that seem to have the high affinity for the organic contaminants, they're the same kind of stuff that you find in certain zeolites that people are thinking about using for like water treatment, for example. So,
cool. So we have it.
Thank you. I was wondering about the case of seawater, actually. So, like, how the ionic strengths of the water affect the absorption of the organic matter to the minerals? Do you have any idea?
I don't know. We haven't looked at the effect of ionic strength, but we've looked at the effect of the sodium to calcium ratio, right? Because that kind of tends to vary quite significantly. And we know that that affects the interaction between even the kind of soil minerals, right? And definitely you see stabler organic coatings when you have more calcium, right? Which has been hypothesized for a while, right? Like organic matter is negatively charged. Most of the soil minerals are negatively charged. It's been kind of like hypothesized for a long time that if you have more divalent ions, they can bridge between the negatively charged functional groups, mostly carboxylic groups in the organic matter, and the negatively charged sites in the mineral. The mechanism that we see is a bit more complicated than that. It's not just a kind of like cartoonish kind of cation bridging mechanism that people have talked about, or that people usually draw in. But yeah, like the aqueous chemistry, particularly the ratio of monovalence to divalence, seems to kind of help stabilize the organic coatings in general, right?
So I think this will be the final question, Jay.
Hi, thank you for the very interesting talk. I just have one very quick technical question. In your first part, you decomposed the free energy to the entropy and the enthalpy contribution. How would that tell whether the PFAS is absorption is due to the repelled by the water, or they like that water? Like how that would tell you?
Yeah, I mean, okay, yeah. I'm not exactly breaking it down into enthalpy and entropy, right? I know I wrote enthalpy and entropy on the slide, but the breakdown is into kind of like that free energy of adsorption. What component is it from the change in the potential energy of the PFAS itself, right? You know, like I can calculate the potential energy of the molecule far from the surface and near the surface, and that change in potential energy, which is basically kind of like one component of the delta H of adsorption. That's the part of the delta G that's coming from the organic molecule itself wanting to be near the surface, right? And then by subtraction, I can say like all the other stuff, right? The other stuff would be like, I don't know, configurational entropy, also the preference of the water itself to want to get rid of the organic compound, that kind of stuff, right? So like, it's not a breakdown in entropy and enthalpy, it's a breakdown in like the preference of the organic molecule itself, just from a potential energy perspective, and all the other stuff, right, yeah.
Thank you.
All right, so, yeah, so I need to cut it here, unfortunately, but Ian lives here, and so you should track him down, and he'll be in this room and have to exit through that door. So ask him a question. So please join me again in thanking Ian Bourg for. And before you leave, we will have our final HMEI Faculty Seminar of the first year of the Brigger Hall series on May the 5th, which is also a Tuesday, starting again at 12:15. And it will be Sarah Grossman, who's the Barron Visiting Professor in Environment and Humanities. And the talk title will be The Nature of Pediatric Disability Hospitals. So looking forward to seeing you there in May. Thank you.